Chapter 8, Section 4, Temperature and Pressure, Gay-Lussac's Law. Gay-Lussac's law, when the Kelvin temperature of a gas is doubled, and the volume and the amount of gas do not change, then the pressure also doubles. So our learning goal for this is to use the temperature-pressure relationship to calculate the unknown temperature or pressure, assuming the volume and the amount of gas remain constant. So the pressure exerted by a gas is directly related to the Kelvin temperature of the gas. So because it's directly related, if the pressure increases, so does the temperature. Or if the temperature increases, so does the pressure. Assuming that the volume and the amount of gas are held constant in this case. So we would use this formula here. Using the concept that we've learned before, if we have to solve for the second pressure, we're going to get P2 all by itself by doing the opposite sign and getting rid of our T2, and we do that by multiplying through. And so T2 on the top here, T2 on the top here, and we see that we're going to have P2 equals P1 times T2 over T1. Now let's use some doing some calculations here. A gas has a pressure of 2 atmospheres at 18 degrees Celsius. What's the new pressure when the temperature is 62 degrees Celsius? Now remember, assuming that the volume and moles remain constant. Well, remember, this is a direct relationship. So if the temperature increases, so will the pressure. So your answer is going to be more. Well, let's just see exactly how much more. Well, our temperatures, remember I had mentioned that in the gas section, we must convert all of our temperatures to Kelvin. So first of all, the 18 is 18 plus 273, which is 291. And our second temperature is 62. So 62 degrees Celsius plus 273 is 335. Now then, since they want to know what the second pressure is, so second pressure is P1. Since they gave it to us in atmospheres, we can tell it to them in atmospheres. So we have 2 atmospheres times our second temperature divided by the first temperature, the 291. So when we do that, that answer ends up being 2.3 atmospheres, which is exactly what we predicted, that it would be a higher pressure than the original pressure. So here's another problem. See if you can do this. Press pause and come back. A gas has a pressure of 645 torr at 128 degrees Celsius. What's the temperature in degrees Celsius if the pressure increases to 824 torr, assuming that volume and the amount of gas remains constant? Well, you go, well, do I have to convert the torr to anything? No, because we have torr in both places, so those labels will cancel out. Now then they want us to find T2, so that means we've got to rearrange our equation to solve for T2. Let's also remember the concept. It's a direct relationship, so if we increase the pressure, so will our temperature. Our temperature will also be increased. So let's solve the problem. First thing we need to do is convert from degrees Celsius to Kelvin, so T1 is 128 plus 273, which is 401. Now then, we need to rearrange to solve for T2. We already talked about how to do the rearrangement. Another time it would be a cross multiply and divide, and then you would solve for that. So here's our T2. So our first T1, 401 Kelvin times 824 torr over 625 torr. So we get 512 Kelvin. Well, you got to convert that back to Celsius because that's what they ask for. So So let's go 512 minus 273 is 239 degrees Celsius. So yes, it is what we predicted. We predicted that there would be an increase in temperature, and that's exactly right. Now, explain why water boils at a lower temperature in the mountains than sea level. Using this particular concept, well, the atmospheric pressure in the mountains is less. Up there high. Why? Because there's less atmosphere up there, so the pressure's less. It's less at sea level. It's less than at sea level. So that means the vapor pressure, the ability for the water to go from the liquid into vapor, it is going to be able to reach the atmospheric pressure at a lower temperature, which means it's going to be easier for it to boil. So it boils at a lower temperature. Now, it doesn't mean that it's hotter. It just means it boils at a lower temperature. So if you have ever tried to, boil potatoes when you're out, if you're out camping or vacationing up in the mountains at like Flagstaff, and it takes forever to boil those potatoes, well, that's because the water is boiling at a lower temperature because there's not as much pressure pushing down on it to keep that vapor pressure lower. So if there's less air pressure pushing down on it, it's much easier for the water vapor to boil. And so it's going to boil at a lower temperature, which means it's going to take longer for you to cook. Here's the analogy. Think about your oven. Now, your oven is not going to vary by the different atmospheric pressure because we're not boiling water in your oven. But let's say that you want to bake some brownies, and you bake some brownies at, just say 200 degrees Fahrenheit. It's going to take a long time to cook those brownies. But if you cook it at the temperature you're supposed to, at like 375, it's going to be done in your 15 minutes. And so the concept here is the same in regards to at the temperature. So when you're boiling the water in the mountains, because the boiling is going to happen at a lower temperature, then it's going to take longer to cook.